Today I'll be going through some graph sketching ideas that can help you when you're given a graph sketch. So here are just some things to consider. So the most obvious, the y-intercept and the x-intercept, and these are when these occur. Well, the y-intercept occurs when x equals 0, and the x-intercept or intercepts are when y equals 0. Onto the domain and the range. So essentially, domain are our inputs, and things we can look out for are restricted values. For example, if we have y equals 5 over x minus 2, we know that x cannot equal 2 since y would equal 5 over 0. And we know we cannot define, we know that 5 over 0 is undefined. Therefore, this will become a vertical asymptote on our graph. When looking at the range, we should consider things like the bounds of our domain. So if we have minus 1, less than x, which is less than 1 in the graph, sine x, for example, we should look what happens when our inputs are minus 1 and 1. Well, actually, that's wrong, because minus 1 and 1 is the range of our sine graphs, so we can scrap that idea. Also, for our range, we should look at what happens when a graph approaches its vertical asymptote. For example, with 5 over x, y equals 5 over x. As x gets closer and closer to 0, what happens? So if x is something like, if x tends towards 0, y would be just a really large number, which is also the same thing as saying y goes towards infinity. Onto our even function now. Well, what is an even function? An even function is a function that can be reflected in the y-axis, and you'd get the same function. For example, y equals x squared. Have a look at y equals x squared. There's a line of symmetry at x equals 0, which is the y-axis, and an even function is defined as when f of x equals f minus x. And let's say we had function of x which equals x squared. If we had f of minus x, we'd have x squared, not cubed, x squared. Onto an odd function. And this is where minus f of x equals f minus x. And an odd function can be rotated 180 degrees about the origin. Let me give you an example. If we have f of x equals x cubed, f of minus x equals minus x all cubed, which is equal to minus x cubed. And we know this just is equal to minus f of x. So if you sketch x cubed, have a shape like this, and we can see the first quadrant here has been reflected 180 degrees about the origin into the third. We can also see this as a reflection in the x, reflection in x followed by y, or vice versa. So if you reflect our first quadrant in the x-axis, we'll have something like this, then the y just overlap onto the part of the graph in this quadrant. Now our vertical and horizontal asymptotes. Well, we have vertical asymptotes when our function is undefined. For example, if we have f of x equals 2 over x minus 2, or let's say x minus 5. Our function is undefined when the denominator equals 0, so when x minus 5 equals 0, this is when x equals 5. And here we have the vertical asymptote. Now if you look at our horizontal asymptotes, this is where x gets really large. I'll consider an example in a moment. Just let me get back to that. Last point is stationary points. So we should always differentiate our graphs and equate the gradient function to 0 to find our stationary points. We should also be determining the nature of the stationary points, whether they're local minimum, maximum, point of inflection. We know this by finding the second derivative. So d2y over dx squared is greater than 0, means that the point is a local minimum. For example, y equals x squared. If you differentiate twice, we get 2, and this is larger than 0. So we know here that this is a minimum. This is also a dummy case if ever we forget. And we can just see that our turning point is indeed a minimum. Taking the converse, d2y over dx squared is less than 0, means that our stationary point is a maximum. For example, y equals minus x squared, where the second derivative is minus 2. We have a maximum. Last thing to consider, point of inflection. And d2y over dx squared equals 0. So when d2y over dx squared equals 0, we potentially have a point of inflection. The way we test for point of inflection is by gradient testing. So imagine the point minus 2. What we do is we test for gradients of points right beside minus 2. So in this situation, we do check for that minus 1, 1.9 and 2.1. Minus 1.9 here and minus 2.1 here. And yeah, if the gradient at both these points is either both positive or negative, there will be a point of inflection. Otherwise, we'll just have a maximum or minimum. That's all for the graph sketching ideas. See you in the next